So, good evening, everyone. I hope you had a nice day and a good start of the week. And thank you for joining us today. So my name is Marwa Shafi, and I'm a faculty with the Electrical Engineering program here at NYU Abu Dhabi. And I'm really happy to introduce our speaker today, Professor Mohamed-Slim Alouini, who is a distinguished professor of electrical and computer engineering at King Abdullah University of Science and Technology in Saudi Arabia. So before joining KAUST, he served as a faculty at the University of Minnesota and then at Texas A&M University in Qatar. He received his PhD from Caltech, and he's currently IEEE Fellow, Optica Fellow, and WWRF Fellow. So Professor Slim is a communication theorist. I will just say a few words about you. And his current research interest is in addressing the technical challenges behind the uneven distribution and access to information and communication technologies, especially in rural and remote areas. So his talk today will be on 6G. We are now in this amazing phase of speculating and brainstorming, both in academia and industry, about what 6G would be. So Professor Slim will give us his vision about the next generation of wireless communication. So thank you for accepting our invitation, and I hand you over to Professor Slim.
Okay. Thank you, Marwa, for this very nice introduction. And of course, I would like to thank you, NYU Abu Dhabi Institute and the Dean of Engineering, for inviting me and for giving me this opportunity to share with you some of the work that we have been doing at KAUST, and also some of our perspective and vision for emerging and future wireless communication systems. So, as Marwa mentioned, we are in this very interesting phase where we are collectively, both in industry and academia, brainstorming and thinking about what 6G might be, would be, should be. And it's a 10-year cycle. You know, you probably have seen that. Every 10 years, we deploy a generation of wireless communication system, and now we are aggressively, deploying 5G. Probably UAE is ahead of many other countries. And as this deployment is happening, this kind of vision and perspective is going in the labs, and people are thinking about 6G. And of course, usually what you want to hit is pushing the envelope type of research. How can we go faster? How can we lower the latency? How can we increase the density of connect device per meter square? That's what a lot of researchers are focusing on, including some of the great momentum that's happening now in Abu Dhabi, between here and also in TII. That's often the focus. But what I would like to talk about today about some maybe things that sometimes are viewed as side type of research topics, but I would like to advocate that these issues are sometimes as important, and we should also spend quite a bit of resource and research time to try to investigate these issues. So one of the issues is that came out of 5G deployment and or one concern, if you will, is energy efficiency. 5G is great, is giving us super high speeds, but this is coming at the expense of this network being quite greedy from a power consumption perspective. And when we talk about being greedy, it's bad from two perspectives. It's bad from the fact that essentially, you have all the CO2 footprint, and we are, of course, at a time where we need to kind of think about climate change and about CO2 footprint, but also because, it makes the bill of mobile network operator high. So there is an effort, or let's say there is a desire also to make this network more energy efficient, which means they are supposed to continue delivering the same kind of performance, sometimes maybe even performance, but essentially it has to be done in a more energy efficient fashion. That's not a topic I'll be touching upon today, but being kind of a large audience type of talk today, I just want to kind of point out to this important issue. The second important issue, and this usually make it to the media, especially every time we deploy a new generation of communication system, is EMF radiation. Often there is this concern about, is 5G going to make us sick, or are we going to get cancer out of these radiations? And of course, this is an important topic, and although, again, it's not really the main focus of today's presentation, it's a topic that we need to kind of take seriously. And as we move to the next generation of wireless communication system, we want to make sure that essentially we are still going to make sure that these networks are operating in what I would call a safe regime. The third topic, which is actually more the focus of today's presentation, is connectivity divide. We tend to forget, especially if we live in very well-connected environment, that about now 1/3 of world population, it used to be 1/2, we are now roughly at 1/3. 2 billion people are either not connected or underconnected. So by underconnected, we mean by that people who are still living on a 2G type of connection. And with 2G, you are not fully taking advantage of the benefits that come with the internet. The reasons are many. I will talk about some of them as we move forward, but that's an important issue because it's an issue that we need to address, in particular as part of this important, of course, development. As you know, a few years ago, many countries, the United Nations actually adopted these so-called Sustainability Development Goals. I'm sure many of you are familiar with these so-called SDGs, 17 of them, quite noble goals that are trying to make the world a better place, by improving the quality of education, quality of health, reducing inequalities, and so on and so forth. So in this context, so some of us that are quite active in wireless communication research are advocating that 6G, in contrast to the earlier generation of wireless communication system, which you can say were essentially driven by profit and financial consideration. Nothing wrong with that. To be sustainable, you need also to be financially successful. But you want 6G to be driven, at least in part, by these United Nations SDGs, which means you want to address the concern that came out of the previous generation. Number one, you want to be more energy efficient, deliver the same quality of service with much less power, with more renewable energy. That's one of the goals that you would like 6G to achieve. Goal number two, make sure that you are still operating in a safe regime from a health perspective and from an environmental impact perspective. Number three, we want to be more inclusive. We need to connect more of the unconnected. As I told you, this is a global problem, and in a way, COVID-19 showed that, digital divide or connectivity divide is the modern face of inequality between the have and have not in this digital context. Now, we want also to make sure that these networks are more secure and preserve our privacy, especially that on a daily basis, we are relying more and more on our smartphone. Imagine yourself now living without your smartphone. I'm sure most of you will not kind of see yourself, basically working or even like having daily type of a transaction without having access to your cell phone or your smartphone. And finally, again, because we rely so much on our phones and our daily life and on connectivity in general, we want to make sure that these networks are resilient, are robust, and are dependable. Before, essentially, you cannot afford to have, let's say, a power outage, a blackout. This is very well known that, it's a bit make the news if you have any kind of power outage in a city. But now I think we are going to be at a time where when we have a serious also network outage, a lot of operation and daily kind of routine can be stopped, which means we need really to gain in resilience. So I'll be focusing mostly on this, how we can bridge the digital divide, what kind of technologies. The talk is relatively at the high level given the audience, but I will try to maybe insert some technical slides, in particular from kind of colleagues coming from wireless communication background. So I think I'm motivated enough why connectivity is important. It allows us, in a way, to break this vicious cycle of digital divide, where essentially you can, by connecting remote region, provide better education, can be done remotely, better health services, smart agriculture, and so on and so forth. But there is another important aspect that we advocated for in this paper that was published a couple of years ago, is that actually it can help trigger a counter-urbanization process. Many of us end up living in urban environment because this is where essentially there are job opportunity. This is where people feel there is a better quality of life. But actually, if you connect people from wherever they are, then obviously maybe, or let's say maybe, some people may choose to relocate to a suburban, rural area and work from these less congested, less polluted type of environment while having a good quality of life and access to good services. So what we are trying to say here, we can move from you can call it the narrow concept of a smart city to something broader that you can call smart hamlet, smart village, smart rural area, or smart living, where basic connectivity will seamlessly allow you to work for and access information and access all kind of other kind of service and entertainment remotely. One other important aspect that is actually under the same umbrella is this notion of resilience. If you invest in research, in connecting the unconnected, and directly you are helping developing technology that can be used on demand when connectivity is lost because, for instance, of a natural or a man-made disaster. And that's a theme on its own. It's called post-disaster communication. Like, unfortunately, what happened over the last few days, as you all know, this earthquake. Often, base stations are down, connectivity is down where you need it most, especially for the first responders. So disaster operation is an area where basically disaster emergency communication is an area that has some good connection with connecting the unconnected type of research. You are in a very high, let's say, hotspot type of environment, like a concert, a final of a soccer tournament, and you have very high capacity. You start being disconnected because the network is not dimensioned to deal with that capacity. So you need to provide maybe some extra capacity just for a temporary type of situation. It falls in a way under the same umbrella. You send a bunch of scientists or adventurers in the middle of nowhere and you want them to stream information continuous base. It falls also in the umbrella of connected and unconnected. Of course, military missions sometimes operate in an environment that are not well connected, and they need that type of research to a certain extent, although this is not really our focus. One final motivating slide. I have been talking mostly here about connecting unconnected, and meaning by that connecting people. But once you have that umbrella, once you have that infrastructure, automatically you can start connecting machines, sensors, actuators, and that allows you, in a way, to enable many other interesting kind of scientific type of, let's say, exploration or monitoring. Like, for example, if you think of a world where basically you have sensors everywhere, even in hard-to-reach areas, when you can collect information in real time and process information, you may essentially target or maybe achieve better modeling for climate change monitoring, for example. So what is one of the main challenges behind this connectivity divide? In technical terms, we call that the backhaul challenge. So what do we mean by that? That's illustrated by this diagram, where essentially we are here showing the quality of experience as function of the cost per user, and we are focusing on remote low population density areas. So we all know the quality and the speed that come with optical fibers. That's how we get internet in our homes if you are super high connected. But obviously optical fiber will not work. Why? For this type of scenario, because it does not make much business sense to dig, lay hundreds, if not thousands of kilometers of fibers in order to reach these typically sparsely populated, hard to reach and low-income environment. Just from a return on investment type of perspective, it does not make business sense, and that's why mobile network operator will never invest in these remote regions. Now, obviously, satellite is the way to go if you want to kind of achieve broadband, broad coverage, but classical geostationary satellites have been designed for more broadcasting operation, like TV, like you're just receiving. It's not for two-way, basically internet browsing type of activities. And that's why what we are targeting, which I'm calling here the global connectivity holy grail, is how can we get the desired quality of experience from an internet access browsing perspective, but at a low cost per user, even in this sparsely populated type of environment, in order to reach this interesting, you can even call prophetic statement made by Tesla about 100 years ago. If you read it carefully, Tesla was already thinking in a 5G or 6G terms in 1919. Now, the way you can do that is by designing your network in a completely opposite way. We have learned how to design them for urban, by urban I mean highly dense populated areas. When you go into urban environment, what we do, we go and we use what we call small cell. Because we reuse the spectrum and we have enough people that are subscribing, so we can basically increase capacity by aggressively reusing the spectrum. When you go into this rural area, you don't want to invest in more base stations. You want one single base station to cover a large, basically, area. And the way you do that is by gaining in altitude. For instance, one idea that had been proposed many years ago by a few people is to recycle or reuse TV towers. TV towers have been built in the 50s and 60s in many countries, and they are usually strategically located on the top of a hill or a mountain in order to gain that particular coverage. In particular, if you use the low end of the spectrum, you know, the UHF, VHF band, which is allocated for TV, gives you basically a big coverage. So actually, we kind of picked on that idea, and recently we wrote a small magazine paper on this, led by Dr. Ammar Al-Falou in my group. And the idea is we picked one area, we picked just an area in Ethiopia. Ethiopia is one of the countries that suffer quite a bit from the digital divide. And we ask ourselves, what kind of gains we can obtain if we take, you know, the existing TV towers and equip them with some, what we call massive MIMO for people who know this technical term, which is a multiple antenna type of technology. And what we showed in a very simple terms, so in red here, essentially we have the existing base station, which are located in an area where there is a high dense population. So, you know, yellow is very light dense population, all the way to blue is very high dense population. So you look at mobile network operator, obviously they will put their base station in area where there is a high dense population. Now it happens in our area, there are 3 TV towers that have not been used for cellular communication purposes. So we said, let's assume we attach to this tower, assume that you have some backhaul there, and we can talk about that later on, how we can get backhaul. Then basically, you can start covering these areas, and actually we show that out of 200,000 people, we can cover 19,500 more people, which means we go from 4.5% to 14.25%. And actually, for the same, let's say, capex, which means if you choose to relocate base station, in particular in these areas, where you move them to area where there's a high dense population, you can gain further in the number of people you can connect. So this is very, I would say, low tech. There is not much here in terms of innovation, but with that, you can help mobile network operator reuse some of their capital equipment and connect more people in a relatively low cost fashion. But if you don't have access to these towers and you want to gain an altitude, here we get into more research topics. For instance, one area that has been kind of more pursued in the US is this concept of tethered balloon or tethered airships. So these are, you know, aerostat or airship that use the buoyancy principle. So they are filled with basically gas that is lighter than air, for example, helium, and with that they can stay aloft. They can operate at nearly 800 meters, you know, to 1 kilometer altitude. You can attach to them a base station. They are typically tethered, and the tether or the cable is there for 2 purposes. First, to provide power to the base station, and also to create the backhaul to the ground. So you can have a fiber optic access or maybe a satellite type of connection that will allow you to make sure that this access point is connected to the network. And with that, you can create, you know, a cell of few tens of kilometers. You want to gain further in coverage, you need to go higher. And higher means you can, for example, go to, I mean, these last days, many of you probably heard in the news about these balloons, right? So these balloons operate, but for different reasons. Here, these balloons are supposed to be there to basically provide connectivity. They are flying in the stratosphere at 20 kilometer altitude. With that, you can create a base station in the sky that can give you roughly a coverage of, with a radius of 100 kilometers. And the beauty of that is and I'll tell you a little bit more as we progress in my presentation, you can use your standard phone. This is the main difference between what I'm talking about and what probably you have seen in the past. You don't need special phones. The phone that you're using on your day-to-day type of activities will be the phone that will allow you to connect to this HAP. So HAP stands for High Altitude Platform Station. Some people call them also High Altitude Pseudo-Satellites, and that's what it is. It's a flying platform. It does not have to be used only for connectivity. Usually it comes with an altitude and with a budget. By budget, I mean a power, size, power, size, type of, and weight, obviously, type of budget. So they'll tell you have 20 kg with this amount of power, and basically that can operate at 20 kilometers, and with that you can put an antenna, you can put a radar, you can put sensors. So it's a flying platform at a certain altitude, and with that you can customize for your own needs. Now, the ultimate solution to gain in coverage is to use space. And by space, we need satellites. And by satellites, there are three, I would say, well-known families or category of satellite. The classical one, GEO satellite, that probably all heard about it, and these are the ones that are used for TV broadcasting. But if you want to reduce latency, which is often needed for internet browsing and low delay type of application, you know to go lower in altitude on orbit, and you start talking about middle Earth orbit or MEO satellite, all the way to LEO satellite. So LEO is anywhere between, space start at 160, but typically at 600 kilometers, all the way to, like 1,000, 2,000 kilometers. And as an example, because everyone knows about it, usually you heard about, Starlink, the SpaceX, Tesla, SpaceX type of project, but it's not the only one. People probably heard about only Starlink. There are many other competing projects. OneWeb, which is the UK version of Starlink. There is Kuiper, which is the mega constellation preparation by Amazon. It's a huge constellation. Chinese have their own also constellation. Lightspeed, which is a Canadian constellation. So, these are not research projects. These are ongoing projects, and within few years, you will have all these satellites operating worldwide. So the bottom line is to create this seamless connectivity anywhere on Earth, you need to rely on what we call in our jargon integrated space, and by space we mean satellite, air, and by air we mean drones, balloons, glider, all these kind of technologies that are not in the space, at the stratosphere, all the way to maybe above 200-meter altitudes, above a tower, basically, and ground, which is the classical terrestrial network. And again, what I would like to emphasize, this should be transparent to the end user. So the end user is using his or her own standard phone, and he or she doesn't know if she's connected to a close-by base station or connect to hubs that have to be backhauled with a satellite. That's what the network is in charge, and that's where integration is important. And that's the main difference between what we're talking about today and what was talked about at the time when I was a PhD student, and maybe some of you remember this era where a lot of people were talking about teledesic and iridium, and we can offline talk about the contrast or the difference between these projects in the late 90s and what we are talking about today. Now, one last comment, kind of highlighting also the importance of this aerial and space network, is in transportation environment, there is also this interest in going to what they call, or at least what I was told, near space type of transportation, which means flying taxis, flying cars. So if you want to connect these flying cars operating at 200 meters or maybe a little bit above that, either you're going to connect them from the ground, and you may create interference to cellular networks, or you'll have to connect them from the sky. And actually, we did some analysis, and we showed that connecting from the sky can give you a better, let's say, coverage and reduce the handover, reduce the amount of interference on ground network, and actually that can have also this extra benefit. Now, I would like now to start connecting this to some of the research we are doing in my lab, and of course many other researchers are working on similar topics worldwide. So this part of the talk is the title is A Light in Digital Darkness, and I hope you will appreciate why I'm calling it this way. Because one key aspect for us telecom engineers, especially wireless telecom engineers, that we have to deal with is spectrum. Spectrum is a natural resource. You cannot create spectrum. You have to deal with it. And unfortunately, it gets filled very quickly in view of all the competing needs from governments, defense, civilian applications. So you need to manage spectrum. And spectrum is heavily regulated everywhere worldwide and is expensive. So there are multi ways to solve this spectrum crunch. One way is to just migrate towards the higher part of the spectrum. So we are mainly operating now on the RF part of the spectrum. But of course, as you go up, at some point, you will hit the optical band. And when you hit the optical band, we can start talking about optical wireless communication. And that's why I'm talking about light, which is like basically the optics. With light, like fiber optic created a revolution a few decades ago by providing high-speed internet to our homes and our connected cities, we believe that free space optic down the road can create the same revolution for the wireless world. That's basically fiber over the air. So you take a laser, instead of using it to transmit over a fiber, you use the laser to transmit over the air. Benefits are clear. You cannot beat optical from a speed perspective, so that can give you easily, with a very low effort from a signal processing, communication, let's say, techniques perspective, your terabit per second, let's say, if that's kind of your target. But of course, it comes with challenges. Some of the challenges very much sensitive to weather condition. Fog in particular can be a killer for free space optics. And the very other important aspect is alignment. When you have a free space optic link, we are talking typically for point-to-point communication, which is great for backhauling. But as soon as you start having some vibrations, you get the misalignment and you lose essentially your connectivity. So you can go from 1 terabit to essentially nothing. And obviously, you don't want to deal with this kind of unreliable type of system. Whereas when you are dealing with RF systems, is usually more tolerant to misalignment, vibration, and this kind of type of basically disturbances. So the idea here is FSO, by the way, or free space optic, is not a new technology. It has been there for some time. It struggled to make an impact on terrestrial network for the reason I mentioned. Mobile network operators tend to go for always easy solutions that can be scaled at a low cost, and free space optics require a little bit of extra caution, in particular in terms of tracking and alignment, but also in terms of how it performs in different kind of environment. However, for airspace type of application, we believe there is an interesting niche where FSO can bring basically unique advantages. So one paradigm we are pursuing is this paradigm that is known as a hybrid, very high throughput satellite. I add here site diversity. So what do I mean by that? And this is in the context of connecting the unconnected. So remember, the idea, you want to go in altitude. You want to have this base station operating at high as possible, so that it allows you to give this visibility wherever you want to connect. So a very high throughput satellite can give you that. So this is a satellite. You can imagine that the satellite can operate at terabit per second capabilities. It has multi-beam, so this is beam hopping type of technology. So the beam is not fixed. It can move around. It can be programmed to move wherever capacity or traffic, we need to absorb some traffic, so you can move the beam wherever you want. So that's the advantage of this kind of beam hopping type of approach. You can use RF. Every beam can carry up to few gigabit per second, and again, it's dynamic. Obviously, the satellite is acting as relay, so you need to connect the satellite to the internet. So currently, we do have some high throughput satellite. Let's not call them very high throughput satellite. They're using Ka band. So Ka band is one particular part of the RF spectrum, but this particular band, is getting congested. Is expected by the early 2030s, that this band, some of it is going to be allocated to mobile communication, to the ground, and some of it can start being used for user link. This is what we call a user link in yellow, which means the user link now is using a different RF band. Ku band is getting saturated, so the Ka band is supposed to move to this user link. And with that, what is a solution that we are proposing to create this backhaul is to use free space optics. So use a laser link to collect satellite to the ground. With, of course, in mind, interesting research that is being kind of worked, again, worldwide now by different groups, how to address the pointing and acquisition and tracking problem. How to make sure the links are always basically aligned and you avoid misalignment or pointing error. How can we deal with bad weather conditions? And that's actually very simple. You use site diversity, which means you don't have a single optical gateway station, and from above, if you like in Europe, there has been some studies, you can look at cloud statistics over the years, and you can place strategically your optical gateway stations. So basically, you make sure that at any given time, the probability of having all link blocked is essentially zero. So it's enough to kind of connect to a single optical gateway station to get your connection to the network. Now, another interesting aspect, and I mean, some of you may be working on cybersecurity, there is an interesting also, I would say, matching point between security and free space optics. Because with free space optics, you can use quantum key distribution that has been used in the context of fiber optics. And with that, you can secure this link. And that's critical, to secure the backhaul, because if you are able to eavesdrop on the backhaul, essentially you can listen to everyone, because everyone has to go to the backhaul. So these are some of the aspects that make free space optics an attractive solution, and there are many companies now worldwide, including Research Center, working on FSO for space and for air type of applications. You can replicate that, the same concept, for very high throughput HAPS. So HAPS is what I told you about earlier, this flying platform in the stratosphere with kind of beam hopping strategy and with the backhaul that can be done in free space optics or using also RF. And with that, you can provide connectivity for maritime application or for rural areas. Actually, in KAUST, and this is a project led by CST. So CST used to be called CITC, for those of you who are familiar with the government agency Saudi Arabia. So CITC, which is now called CST, is the FCC of Saudi Arabia. So that's the regulator, spectrum regulator, but they have many, little bit more kind of part of their portfolio. They also run some demos and some prototype kind of experiments. So there was this experiment done in collaboration with Deutsche Telekom and with stratospheric platform. It's a paper going through the review process now. So we're involved just as part of the design of the experiment and recording some of the results and trying to kind of publicize them. So the idea here is to emulate a HAPS. There was this kind of airplane operating at 14-kilometer altitude. This experiment happened in the, I don't know if you know, the Red Sea Global Project. People know about NEOM, but that's another project. It's like not very far from KAUST. It's a few hours drive from north of KAUST. And the idea is to emulate HAPS using this stratospheric airplane operating at 14 kilometers, not at 20 kilometers, and trying to see how, obviously, it's going to outperform a regular cellular network. So you see here, you have a kind of a terrestrial network, and you try to show that with the HAPS, as you move away from your terrestrial network, the terrestrial network in blue performance goes down in terms of data rate, in terms of spectral efficiency, but the HAPS, given that it's giving connectivity from the sky, it provides a constant good connectivity in terms of data rate and good spectral efficiency, even if you are very far from the terrestrial network. Actually, there was an experiment done during the same day where someone was on the boat. I mean, really, it was, I think, more than 12, I think around 17 kilometers, and that was allowed or enabled a maritime type of communication with a standard type of connectivity or cellular connectivity. And here, I'm just showing you kind of a result was recorded that day, showing that we were able to maintain a very good signal-to-noise ratio, which means a good data rate, even from the boat. So this is, I think, maybe less, I would say, advertised or less talked about type of technology. People talk more about satellite, but HAPS is interesting to me from one important perspective is you don't need a relay on the way. A HAPS is an access point on its own. You use your standard phone to connect the HAPS. Every time you talk about satellite, you need the relay on the way. So when people talk about Starlink, what Starlink provides you is maybe a very small, maybe a pizza box type of antenna, but then you connect to that kind of access point that the antenna will provide you. With the HAPS, you don't need that. Your phone will allow you to connect directly to the HAPS, and the HAPS will connect you to the rest of the network through some kind of backhauling operation. Now, one other topic, I hope I'm doing well on time. I think I'm still right. I have a lot of slides. I will not cover everything. I will stop wherever I have to stop. But I'm just giving you a perspective on different projects now and on how they connect to this connectivity divide. So, I have been emphasizing this kind of connectivity divide for rural areas, remote areas, and how we can reach them by expanding the coverage. But unfortunately, the digital divide does not always touch only this remote, lightly or densely, low density population. It can affect, very close neighborhood. There was some studies, even this is New York, here we are at NYU, right? Even in New York, like an area like Bronx, COVID showed that it's not a very well-connected areas. So it doesn't, then it becomes an affordability problem. How can we reduce the cost of connectivity? Maybe connectivity is available, there are base stations around, signal is available, but it's very expensive for people, given their income, to connect to that particular network. And how can you reduce the cost? So there are different, maybe I'm not sure if TII is heavily involved in that, but there is this open RAN type of movement that is trying to reduce the cost and remove some of the monopolies. But there is also spectrum. Spectrum, as I told you, is regulated and is expensive. It's used by many countries to make money, legitimately, because it's a source of income. And at the end of the day, a mobile network operator will bid, will get the spectrum, and the end user will pay that cost. Now the trick is, if you unlicense the spectrum, if a government chooses, for whatever reason, to choose some part of the spectrum and say that part of the spectrum is free, is unlicensed, with certain regulation, then you can enable some low-cost type of solution. So one potential, deployment relying on unlicensed spectrum is so-called integrated backhaul access. It comes in different forms, but what I would like to highlight here is an integrated access backhaul that can be done over unlicensed spectrum that can reduce the cost. So the idea is, this is not like a cellular type of technology. So you can have a backhaul. You can think of this as, and I will show you an example we did in KAUST. You can have, in the neighborhood here, a good, well-connected area. You have fiber optics, or you have a very good, access from a satellite link. But then you have a low-income neighborhood. So one way you can connect this low-income neighborhood is by creating a Wi-Fi mesh. Like, in a campus here, you create the mesh, and basically every single router is itself, source of information and relay for the next point. And that's why it's called integrated access and backhaul, which means every point is acting as an access point, but actually is helping with the backhaul or the fusion of information through this mesh. So actually, as an experiment or as a demo, in KAUST we did, it was like a few months ago, and it started a long time ago, but took us a lot of time to get all the approvals. Just as a way, there is not much research here, but as a kind of community project that we led with Meta. It used to be called Facebook when we started, to tell you how long it took to get this whole thing. So basically, this is like a map of our campus. It is part of our campus. We have a kind of here the border or the fence. And then in KAUST, we rely a lot, of course, on technicians, on drivers, on gardeners. Many of them live nearby in a worker camp, so it's managed by this company called MAC. And I happen to learn that essentially they have a very poor connectivity. And connectivity there actually is quite expensive. So the idea, I said, okay, while we on KAUST, we are very well connected. We have fiber optic pretty much everywhere. And obviously trying to put a fiber optic link here crossing this highway was expensive. So what we put is, we put a hybrid free space optic millimeter wave link to create like a few kilometer backhaul, 3 kilometers. And then, and that was funded by KAUST. And then Facebook funded this Wi-Fi deployment using one particular IAB or integrated access backhaul technology they came up with at some point called Terragraph. It's a good one, there are a few others. So basically we combined these two technologies and we were able to backhaul this whole campus that kind of hosts about 3,000 workers. And all of it was over unlicensed band. So free space optics unlicensed, Wi-Fi plus millimeter wave backhaul between the nodes here, we have many of them. Were done over unlicensed band. We got all the approvals from the CST. It was a pilot project. With that, we were able overnight, once it was activated, of course, took time to get all the approvals, 3,000 people for free. So until now, they're connecting to the KAUST network and over unlicensed bands. And now we're trying with CST to try to scale this up, to see how we can replicate this over multiple other worker camps in Saudi Arabia. Now maybe that's the only few slides where I will go a little bit more technical, although I will not go too much details, but just, to show you what kind of research we do. How much time? 10 minutes, okay. So, for example, let's take a free space optic link. So one of the major problems behind free space optics is once you transmit is, as I mentioned to you, completely different than transmission over fiber optics. You are dealing with a free space type of transmission that is subject in particular to atmospheric turbulence. And atmospheric turbulence leads essentially to two effects. It leads the beam to spread, and by beam spreading, what you end up having is a blurry image at the receiver end, and it leads to beam wandering. And by beam wandering, that leads to some kind of, image dancing, or if you want, beam dancing at the receiver end, which means misalignment and pointing errors. So these are two effects that you need to deal with. From a receiver end, you have a detector that is supposed to be aligned with the beam, and what you end up having is this fluctuation of the signal because the beam is not perfectly aligned. So you end up having a signal that is not constant, like it is the case in fiber optics. You have always a path loss. You have to live with that. But on the top of the path loss, you have this random fluctuation that really degrade quite a bit the performance of your system. So the whole point of, at least from my perspective, there are people who try to improve the performance of this system. For instance, like for example in RF, and a lot of people doing RF engineering here, we do a diversity type of system. So you try to take advantage of multiple channels in order to capture the signal from a good channel. When you deal with turbulence, you can do that if you space your receiver well enough. But there is also an interesting technology borrowed from the imaging world, like telescopes, adaptive optics. Essentially, you can rely on an array of deformable mirrors to try to kind of, in a way, undo. It's like from a signal and system perspective, the channel is introducing a certain transfer function. At the receiver end, you create the inverse transfer function. So at the end, you get the original signal. This can be done in a post-compensation fashion at the receiver. If you have basically complexity, size, power constraint at the receiver end, you can do it at the transmitter, which means you let's say, deform upfront your beam so that when it goes to turbulence, assume that you have learned what the turbulence is about, you get a nearly pure beam. So our work, and I will not give the details, is about analyzing the performance of this system under certain channel condition. So you look, for example, at a particular environment. It's characterized, let's say, by a certain level of turbulence, by a certain level of misalignment, usually parameterized by parameters. So you assume that you have a certain distribution for that has been validated, of course, based on either a theoretical model or experimental data. And your whole point when you do performance analysis type of work is to, first of all, use the model that are complicated enough to capture the phenomena that you're trying to analyze, turbulence, misalignment, and so on and so forth. But they have to be simple enough to be tractable. So in other words, to be able to conduct some mathematical analysis and end up, like in this case, with a closed form expression of the ouch probability. So the ouch probability, and I'm sure many people here in the audience know what it is a probability that your signal-to-noise ratio falls below a required threshold. Given that your signal-to-noise ratio is a random process that is, perturbed by different type of phenomena, and you assume there are different distribution and that characterizes phenomena, and you want to basically get a closed form expression for this ouch probability. So this is a recent paper where we're able to analyze exactly the performance under gamma-gamma type of turbulence. This is like one famous model that is used in the context of turbulence. And the pointing error, where we assume vibrations are Gaussian in both horizontal and vertical dimension with different strength. And why it's important, because at least from a mathematical perspective, there are little changes that have to happen in your analysis when you assume imbalanced type of vibrations. In the case of balanced vibration, you can even get simplification. So the whole point is to give engineers that deploy the system these kind of formulas so that essentially they can test for different values and have a feel on how the system will perform if deployed. But of course, when you go to practice, you may face extra difficulties, but that can be basically a first starting point. We did also the same type of calculation for different kind of model. The results were a little bit more complex, but still we're able to achieve some analytical results in this paper. So, for example, with that, you can start kind of getting some intuition about how things perform, and actually you can match this kind of analytical intuition or the analytical conclusion with some of the experimental results. So what we have shown here, for example, first of all, because we were able to capture the effect of that optics. So by the way, this is just outage probability as function of altitude. And obviously, the higher you go, the higher the outage, because you have to go through, essentially more distance of the atmosphere, and that's kind of come at the expense of more turbulence and worse performance. What we are showing here is that with adaptive optics, we see these kind of squares. You can always do better than without squares. The outage probability is lower for a fixed altitude. And one interesting thing we have shown, and that has been also demonstrated experimentally, is that essentially the downlink will do better than the uplink. And the reason is intuitive, due to the fact most of the atmospheric turbulence tend to basically be in the lower part of the altitude, in the lower altitude of the atmosphere. So essentially, when you have an uplink, by uplink I mean transmission from the ground to space. So as soon as you transmit, you get hit by strong atmospheric turbulence, so you start being subject to this beam wandering and beam spreading, and that's why cumulatively you have a bigger effect. On the other hand, if you do a downlink, which is from space to ground, initially you have atmosphere, turbulence is not that strong, so basically you start with a good, let's say, initial condition to a certain extent, and eventually when you hit the atmosphere down, then basically you start being subject to this spreading and wandering, and overall the end-to-end kind of result is that downlink perform better than uplink. And now another interesting result is that if you establish a horizontal link, meaning by that not ground to space or space to ground, but rather space to space, then obviously above a certain level, above 20 kilometers, the effect of atmosphere is not there anymore. And that's well known because atmospheric turbulence is there where there is atmosphere. When you move to stratosphere, you are above weather, you are above atmosphere. And that's why, including actually satellite, LEO satellites, many of these space-to-space communication eventually, in my view, will be done using free space optics, because you have high capacity link without having to suffer from the atmospheric turbulence that unfortunately is still there for terrestrial or ground to space, space to ground type of application. But as soon as you are above atmosphere, you start having very good performance. So maybe I will skip this. I will just tell you about maybe 5 minutes, 2 minutes. So okay, I will skip all this. I will just give you 2 last slides just to kind of connect this to something else we do at KAUST. So, which is also related to connect the unconnected. Another very important aspect, and this actually, if I was not in KAUST, probably I wouldn't have worked on this because it's a very, very small niche area, which is underwater and maritime communication. So you may know that 71% of Earth is covered with water. And actually, and I was very surprised when I heard about that, is only 5% of this underwater world is discovered. So there is a lot to discover underwater. Maybe like we don't know very well space, we don't know very well the underwater world. So when you talk about underwater discovery, for a variety of applications, scientific data collection, underwater exploration, monitoring, like you have a pipeline and you want to make sure that the pipeline is up and running. Of course, there is always military use for these kind of things. But this world of underwater system engineering, part of it is about communication. And communication has been done classically always with low speed acoustical communication that give you the range, but they suffer for quite a bit from basically delay and of course very limited data rate. So one thing we started a few years ago, it's an interesting collaborative project involving faculty from computer science, from marine science, from electrical and computer engineering. And the idea was to use also free space optics. Different than the one we use for terrestrial application, because in terrestrial application, you operate in the 1550 or near infrared band. But when you go underwater, you need to rely on basically green or blue type of wavelength, because depending on the turbidity or the visibility underwater, with that you can achieve very high speeds, but essentially with a relatively small range. So we're among the first to get into this. I mean, now it was 5 years ago. Many people picked up on that. And we were able at some point to hold the world record. And this project, I was doing the theoretical part, but there was like my colleague who was leading from the experimental side, Professor Boon Oy. So in his lab, we achieved many interesting experiments. We were able to transmit a gigabit per second over a few meters all the way to 20 meters. And we combined that also with acoustical communication to gain a range, or multi-hop free space optics underwater to be able to achieve long-range type of transmissions. So I will conclude with that. So we had the project, it ended unfortunately, and hopefully we'll get some extra funding to revive this project. And this was a paper that was published a couple of years ago. We called Aquafy. It was led by Professor Bassem, and Boone, myself, like as PI, were involved. And the idea was to provide Wi-Fi type of quality underwater. And the whole point is, again, to use your standard phone. We don't want to have specialized equipment. So the whole project was about, you have kind of your phone, you put it in a certain enclosure, and then you use a Wi-Fi access point, and then you have a backhaul through a laser link that connects to the boat. And we were able to kind of do an interesting demo within a KAUST environment. So with that, I think I don't have time to cover all this. I would like, again, to thank you for this opportunity. What I would like to emphasize that we want 6G to not only push the envelope from a technology standpoint and go for higher speed, lower latency, a higher number of connect devices per, let's say, meter square. We want 6G also address some of the important sustainable development goals, and in particular, as I try to focus today on connecting the unconnected. And in that context, air and space network can be useful. And free space optics also is a technology that struggled quite a bit in the terrestrial world, but hopefully there is a niche for this technology and for the researchers that invest quite a bit of time and research and effort over the last few decades to make this technology more viable, to basically be rewarded and start using this technology for more of a mass scale. So with that, I would like to thank you, and I'll be happy to take some questions.